Hey everybody, this is Chemical Bonding for AP Chemistry in 10 minutes or less. This video is meant as a refresher on only some of the major topics in Unit 2 of the 2021 version of AP Chemistry. It's intended for students who have already learned the material and beginning to study for the AP Chem exam. For anyone that cares, this video will roughly cover the following topics from the AP Chemistry course and exam description. The things that I don't talk about will be covered in a subsequent video. Let's get started. So of course the overall topic here can be summarized in one word. That word of course is bonding, but what we're actually talking about are chemical bonds, which are the very strong bonds that occur between atoms and create new substances. The AP Chem exam also will sometimes refer to these as intramolecular forces. So let's start off by listing some of the types of chemical bonds that you can expect to see. First, we've got covalent bonds, ionic bonds, and metallic bonds. You can always tell which of these three types of bonds are going to occur between two or more atoms by looking at the electronegativities of the atoms involved in the potential bond. If both of the atoms involved in the bonding have very high electronegativity values, that means neither atom is going to be willing to give up or lose its valence electrons. So what those atoms end up doing is sharing those valence electrons in what we call a covalent bond. If one of the atoms has a very low electronegativity, like this metallic element sodium, and the other one has a very high electronegativity, again like fluorine, then that means the sodium is going to completely lose its valence electron and the fluorine is going to completely gain it in what we call a transfer of electrons, creating a cation and an anion. The resulting ions are attracted to each other in the formation of an ionic bond. And lastly, if both of the atoms have very low electronegativity values, like if there were two or more sodium atoms, they're still going to lose their electrons, except those electrons don't really have a high electronegativity atom to gain them. So each of my sodium atoms becomes a positive cation, but those electrons that have been released don't really have a place to go, so they end up sort of floating freely and moving back and forth between the atoms. Now let's talk about how we can make relative comparisons between the strength of one bond to another. When comparing the strengths of covalent bonds, there's two factors you have to consider. The first is the length of the bond. The second is the order of the bond. So when you're looking at the length, the longer the bond is, the weaker it's going to be, and conversely, the shorter it is, the stronger it's going to be. The order of the bond, remember, is a numerical representation of whether that bond is single, double, or triple. So you'll have bond orders of 1, 2, or 3 respectively. If there's resonance, you can also average those bond orders together and end up with bond orders that are decimals. And the purpose is that when it comes to the strength of the bond, the higher the bond order, the stronger the bond is going to be. The lower the bond order, the weaker it's going to be. Since ionic and metallic substances are both made of ions, their strengths will both depend on the same factors, that is the magnitude of the charges and the sizes of the ions themselves. So you'll get stronger ionic and metallic bonds when the charge magnitudes are greater and when the ion sizes are smaller. Here's a common way that you can see some of these factors modeled when it comes to metallic substances. We'll fill this out for a sample of solid metallic sodium. So each of these 9 circles that I've drawn represents the sodium atom. So I'm going to go ahead and begin just by labeling each of these with an Na. Each sodium atom has one valence electron that it's going to lose, which means since I've drawn in 9 sodium atoms, I need to draw in 9 valence electrons. I'm going to draw those valence electrons here just as little dots. You'll notice that I didn't really put these free valence electrons in any particular spot, and that's because in metallic bonding, those electrons become delocalized from their original atom and then are free to move around within the solid structure of the sample. Sometimes it's helpful to even represent that motion by drawing in some little arrows around each of the valence electrons to show that those electrons are free to move. We might also want to consider the charge magnitudes here. Since each sodium lost one valence electron, each sodium attains a charge of +1, so not a bad idea to go through and label those as well. Some important vocabulary terms to remember in connection with metallic bonding: the fact that those electrons have been delocalized, creating what is sometimes referred to as a sea of electrons. And lastly, these metallic bonds are often referred to as non-directional, since each of the cations is sort of attracted to the space that surrounds it, since that space is negative and full of these delocalized electrons, as opposed to being attracted to one particular negative point in space. For ionic bonding models, you'll see similar setups of neatly organized rows and columns. Let's fill out this one for a sample of solid sodium chloride. So within that solid structure, you'll see alternating cations attracted to anions in this repeating regular structure. This type of arrangement is often referred to as a lattice structure. I also like to point out here that for both ionic and metallic substances, you do not form molecules, so you should not be drawing Lewis structures when modeling this type of bonding. In fact, the only time we should be creating Lewis structures is when creating models for covalent bonds, since it's in covalent bonding that we actually form molecules. Now there's lots of different methods you'll find out there in different textbooks and videos online about how to draw Lewis structures. I'm a fan of a series of 6 rules that if you follow, will draw a really decent Lewis structure every single time. So here's that list of 6 rules that I prefer to follow, and I'll briefly show you how each of these works as we draw the Lewis structure for sulfur dioxide, SO2. So the first thing I'll do is arrange the atoms and count up the total valence electrons. Sulfur atom in the middle, the 2 oxygens symmetrically surrounding. The total valence electron count here is 18. Next, I'll start by putting in single bonds to attach each atom. Each of those single bonds has 2 electrons in it, so the 18 I started with is now down to a total of 14. Next, we'll give octets to the outside atoms first. That means each oxygen has to have 6 more electrons plus the 2 already in the bond, give it 8. After doing that for each of the oxygens, I've used up 12 more of my valence electrons, leaving behind only 2 at this point. We're up to rule 4, which tells me that extra electrons will go to the central atom, so those last 2 get dumped on the sulfur. Rule 5 says to make double or triple bonds if needed. The if needed part comes into play for central atoms that have less than 8 valence electrons. Here my sulfur only has 6. I can't leave sulfur with only 6 valence electrons. I fix that by selecting any random pair from one of my outside atoms and moving that in to make a double bond. Now my sulfur atom has a full octet as well, and this is considered a complete Lewis structure for SO2. From this point, the AP question might also tell you to consider formal charges, so you might see that you could actually get a better distribution of formal charge by taking one of these outside pairs from the other oxygen and moving it in to get a double bond on both sides of the sulfur. And what you're left with should be a pretty accurate representation of how the electrons in sulfur dioxide are distributed in real life. Once you've got that Lewis structure drawn, there's lots of other analyses you can now make relevant to your molecule. One of those is Vesper shapes and hybridization. Let's go through some of those common molecule shapes now. If your molecule has 2 domains that will be linear in shape with a 180-degree bond angle, that central atom will also be sp hybridized. 3 domains is trigonal planar with bond angles of 120 degrees. Here the central atom is sp2 hybridized. 4 domains gives a tetrahedral shape with 109.5 degree bond angles and a central atom that is sp3 hybridized. If there's 5 domains, you'll get a trigonal bipyramidal shape with 120 degrees between the equatorial positions and 90 degrees between an equatorial and an axial. And lastly, with 6 domains, you'll have an octahedral shape with 90-degree bond angles between all 6 domain positions. From that Lewis structure, you can also determine the polarity of your molecule. First, check to see if the molecule has polar bonds, and then check to see if those polar bonds have an asymmetric arrangement. If both of those things are true, then your molecule has a net dipole and will be polar. Lastly, you can also spot resonance structures here if you've got double or triple bonds that can be moved to different equivalent positions within the molecule. And that wraps it up for chemical bonding for AP Chemistry in 10 minutes or less. Thanks for watching.